This is a slide that I use a lot. I just like to point out that we have, in these new sort of modern systems, we have multiple levels of hardware that we need to optimize for. Where this first presentation is going to focus on is mostly on the core and sort of up to the node level optimization. But of course, you can get beyond that and start talking about the network, particularly in a system as large as Theta. I am not going to cover that today. And at the core socket and node level, you have different things that you need to worry about. At the core level, you typically care about specifics to the ISA, things like the vectorization and so on. At the socket level, it's more about your level of parallelization within shared memory. And once you get beyond that, it's more related to shared resources, things like your I/O or local memory accesses and so on and so forth. And at Intel, we have a whole bunch of tools that can help you cover all of those. My talk is not going to focus on this at all. I'm just going to talk a little bit about compiler reports for vectorization. But if you have an interest in optimization at one of these particular levels, these are tools that you could use to explore, and most of these are available in Theta. And actually, my colleague Paulius was talking about VTune yesterday. Right. So let's move on and talk a little bit about CPU basics. What you have here in Theta is a Xeon Phi 7230. That's essentially a 64 core processor that has up to 4 threads per core. So it gives you 256 threads of possible for execution. It comes with 16 gigabytes of MCD-RAM on chip. This is a high bandwidth type of memory that we'll talk a little bit more later in the presentation. It is a single socket node. You don't have issues with remote memory access from one socket to another, as you might have in other systems. And you don't have that PCA bottleneck node there is related to the previous generation of Xeon Phi. There was a breakout card on PCIe. That's not a problem with Knight's Landing. Overall performance is up to 3 teraflops of double precision. As usual, that's going to be extremely hard to get. That's actually a theoretical peak. You'll be hard-pressed to get close to that. And memory bandwidth to the MCD-RAM, it's on the order of 400 gigabytes per second. And depending how you configure the memory and specifically what you're doing, you can get really above that, or you can get significantly below that, as usual. And what I'm going to do is, after I talk to the hardware for a little bit, I'm going to also discuss the memory subsystem and all the options that you have there. So I'll go into a lot more detail in that part. The socket itself is made up of 32 tiles in this case. It says up to 36 tiles because other SKUs, other parts can have more active tiles. On Theta, you have 32. Each tile is composed of a couple of cores and a shared L1. These tiles are connected with a 2-dimensional mesh interconnect that handles all the core-to-core communication. And you have 2 DDR memory controllers for a total of 6 channels, 3 per controller. That should give you around 90 gigabytes per second to DDR when you go to DDR4. On the MCD-RAM side of things, you have 16 gigs of this MCD-RAM memory. This is memory that is attached to the chip. It has 8 embedded DRAM controllers, and the total is, as I mentioned before, around 400 up to 450 gigabytes per second. If you get anything beyond that, then I would be careful with the benchmark that you're running. So this is basically what the socket looks like, right? So we have this 2-dimensional distribution of tiles, each of them with 2 cores. And we have 2 different memory controller systems, one dedicated to DDR4 access, one dedicated to MCD-RAM access. If we look at each of those tiles specifically, you have 2 cores with a shared level 2 cache of 1 megabyte. There is a CHA, which is a caching home agent that handles a lot of the mesh traffic for core-to-core and tile-to-tile communication. And the way that these level 2 caches are kept coherent is through a distributed tag directory. And the way that the coherency traffic flows through the chip depends on the memory configuration that you have. And on Theta, you actually are quite lucky because you can on-demand request a node with any specific memory configuration that is supported. There's some default queues and some default setups, but you can also request a different one, and I'll cover that later. That massive protocol is just a slight improvement on the, well, probably some architects will be throwing things at me if I say slight, but it is an improvement on the messy protocol that we normally use. It just helps with keeping the coherency traffic sort of efficient in a sense. And the core details, we could go into a lot of sort of numbers, but at the end of the day, there's really only a couple of things that matter. You have two caches for instruction and data, both 32 kilobytes, 8-way. The one thing that is really important and that I don't know that everybody realizes if they haven't run on KNL before is that you have 2 vector processing units per core, which you can issue 2 on every cycle. But only one of them supports legacy code. And legacy code is defined as anything that is not AVX512, right? So if you were running something that was previously compiled with SSC and you didn't want to rebuild it, it would run, but you would only be using one of the 2 VPUs, and you would be leaving about half the performance on the table, right? So that's something that is important to understand. Now, I just mentioned AVX512. So what is AVX512? Well, this is the Intel vector extensions, 512-bit. This set of instructions is not just about increasing the vector length. So it does double the vector length to 512 from AVX2, but that's not the only thing that it does for you. It has 32 vector registers, but on top of that, it has 8 dedicated mask registers, which means that in many cases, there are masked operations you can execute where you're not using an additional 1 or 2 registers just to mask each of your vector registers for the operation. You just use one of these dedicated mask registers to do it. What that means is that you have more operand registers to keep things moving through the system, right? So that's a significant advantage that is sort of behind the covers. When you hear about AVX512, all you hear is, 512-bit, 512-bit. Sure, but that's only one part of the improvements of AVX512. It also has embedded broadcast, which is essentially there are many operations with vectors where you might have to put, say, a constant on multiple elements on a vector, and that's typically done through shifts or through broadcasts. On AVX512, you can embed that into the instruction itself, so you're also saving time and resources. AVX512 is not a monolithic ISA. It is divided in 7 subsets, 2 of which are common to Skylake and Knight's Landing, and that actually contain the vast majority of the instructions, right? So you could just compile against that, and you could run on a Skylake processor, on a Cascade Lake processor, on a Knight's Landing processor, and your execution will work just fine, and you will be making use of most of the AVX512 advantages. There is also 2 that are exclusive to Xeon Phi, and those are those 2 on the top, which are the prefetch and exponential reciprocal, and the names are reasonably descriptive. The prefetch just sort of allows you to do a multi-address prefetch using gather-scatter semantics, which can be beneficial in some cases, and exponential reciprocal, they just have wide approximations for log and sort of reciprocal and a square root, right? And then there's 3 additional for Intel Xeon that deal with other things, but for Theta, that's not really very relevant to you. So you get the benefit of the increased vector depth if you can vectorize your code properly, but also you get significant advantages on other things that help with vectorization efficiency overall. So if you vectorize nicely on nice landing, you could get up to, say, a 16x compared to a scalar. Most likely that's not going to happen because you're going to have inefficiencies in memory loads and so on. If you were in single precision, it would be double that. But this is essentially just because you're using now properly the length of the vector, and you have to and you have two vector units that you can use when you're using AVX512 instead of just one, right? Another way of looking at this is if you're not vectorizing on a KNL, then you're leaving a lot of performance on the table. So it's definitely worth looking at your vectorization. And by now, I'm guessing that most of you are already doing this. But it used to be the case that people did not care about vectorization very much because with SSC and even AVX, well, you get a factor 2 possibly, you get a factor 4 possibly, only in a few of your kernels. So most of the time, the effort that you had to put into making sure your code was structured and effective for vectorization might not have been worth on the overall execution of the program. In this case, it is very critical because you're leaving an order of magnitude performance for some of your kernels out if you don't do vectorization. A quick nested loop example that I'm going to use to illustrate some of the compiler reports. Because you can use Intel Advisor to go very deep into the vector efficiency. But even before you start executing and using analysis tools and whatnot, just the Intel compiler can give you a lot of information on how well your code is vectorizing and the places that you would have to go and do something about vectorization and how efficient the vectorization is. So this is just a triply nested loop. What you can see is I'm suggesting vectorization on the innermost loop with a pragma IBDEP, which is ignore vector dependencies. I'm just parallelizing the outermost loop. And what I'm going to do is I'm going to look at the report from the compiler on this specific loop. If I did not have that pragma IBDEP in green, the compiler will assume that I have some flow dependencies in that loop, mostly because of all that multi-level indexing that you see there. So that's why I put that. But if that wasn't there, what the compiler will tell you is there's an assumed dependency and I cannot proceed, right? So if you use these options, QOPT report phase equals vectorization and QOPT report equals 5, you get a fair amount of information. This snapshot I've had here is just a small part of the total output. I'm going to go through it step by step because there's too much to fit it on a single page, right? So first of all, you see that we have 3 different references to vectorized loops. The first actual 2 messages we get is that the loops have not been vectorized because they're outermost loops. This is pretty common. A regular vectorization pass only vectorizes your innermost loops. Now, the innermost loop has been broken into a P loop, a remainder loop, and a core or main loop, right? You see that in this case, the 3 of them were vectorized. But that is not always the case. In some cases, the compiler will realize that the remainder loop is not worth vectorizing, or it might actually vectorize it with a different ISA in order to make it more effective. But, well, we have a fair amount of information. Now, if I just look at the core loop that was in the middle, this is some of the information that I cut out in the previous slide. So you have tons of information about memory access, vectorization efficiency. So let's break this down a little bit just to see the amount of information you get just from the compiler. So first of all, you can see that this loop has unaligned accesses. This is in principle not a problem. Your code is going to execute correctly, but it's going to incur on some inefficiencies, right? The fact that the execution is not, the fact that the accesses are not aligned is going to require extra work from the runtime to sort of align those before it executes the operation. It also tells me that I have the number of aligned and unaligned loads and stores for the loop. And if you went back to the original loop and counted, all of that seems to match. That's an alignment. So what you could do here is you could go back to the original loop and figure out how to pad it. You would have to be careful because you're going to depend on the number of threads that you're breaking this up into to make sure that each axis, and not just the first one, is aligned. But there's enough information here that you can go to the specific references, and you see that XX and YY. I put that there. You will get a proper reference to the specific array which has the unaligned axis. It's just too long to fit in the screen. A few more details beyond alignment. We're using a vector length of 8, which makes sense for double precision on KNL, since we have 512 bit. The compilers decided to unroll the loop by a factor of 2. Fine, I don't know what heuristic made it decide that, but it probably just means that we have enough vector registers to host 2 loops, and that reduces the overhead from the loop setup itself. So that's probably a good idea. And we get a normalized vectorization overhead of 0.7, which probably ends up probably means that we end up being about 70% efficient at the end of the execution. At the very bottom, you will see those 5 lines that describe a cost summary. And what they're telling you is that if you executed the loop in a scalar mode, you would have this normalized cost of 23. So each iteration of the loop will cost you 23, whatever that is. Think about it as 23 units of time. Once the loop is vectorized in the way that the compiler is doing it right now, the cost should go down to 3.6 units of time. So the estimated speed up based on this is about 5.7. It's not a straight division between those two, because the estimated potential speed up includes also the cost of the P loop and the remainder loop. And so that typically changes that number a little bit. But you can see that we're about 70% efficient, and we're losing efficiency probably because of the remainder. If we didn't have a remainder, we wouldn't have additional cost there, and the unaligned axes that are forcing probably gathers or similar or shifts in the setup. Okay, so that's roughly what I wanted to cover, because we only have a little bit of time. That's what I wanted to cover for vectorization. Very important. You can get a ton of information just from the compiler. If that's not enough, then you can use Advisor, which is already installed on Theta, and you can dig as deep as you need to identify specific problems. Now, let's move to threading, because I want to have enough time to talk about the memory modes at the end. But if you have any questions at any point, just stop me. Can you say that louder? Can I what? Can I? Oh yes, so, I'm sorry. Yeah, the slides should already be in the directory that they posted before. So there should be PDF files of both presentations. And if you need the slides, just talk to me later. They're not? Oh, okay. That's odd. I got an update yesterday night telling me that they were uploaded. So if they're not there, I'll make sure that they make it. They should have gotten there with this with this presentation, but we'll fix that if it's not there. Thanks. So in terms of threading, this is a processor that has SMT with 4 threads per core. Now, in the execution pipeline in the core, some of the resources are unique per thread, and some of the resources are shared. So the fact that you can execute 4 SMT threads per core does not mean you should. You might get an advantage from doing that, depending on your code structure and requirements, or not. So not all codes will scale nicely. In my experience, you scale almost linearly when you have a reasonably sensible threaded code until you hit the 1 thread per core, and then you continue scaling, but at a completely different rate, right? Because at that point, you started sharing resources per core, and so things get a little bit messier. Now, you can still get peak performance on the processor with a single thread per core. So having the ability to have 4 threads per core it just gives you more flexibility on how you can handle things. You could also just do pure MPI here, but that typically means that you are allocating a lot of memory for MPI processes, since you have a lot of them on a single node, right? So a better idea would be to do a hybrid combination. If you want to have some idea of how a serial code will thread in this platform, you can use Advisor. In Advisor, there's a part that I'm not going to get into. I just want to give you this slide as an example. You can annotate your code and say, what would happen if this section was parallel? You will do a collection, and then it will show you essentially a simulation of the expected scalability for that section of the code. And you have a lot of knobs that you can tweak with this simulation. Just keep in mind this is still an estimation of your scalability. But you can tweak essentially how much work per thread you have, what your threading environment actually is. It doesn't assume it's OpenMP. It could be TBB, or it could be pthreads, and so on. So this is a good tool if you have absolutely no idea what to do in terms of threading. Now that memory business, that's the part that I find more complicated in OnKNL. Excuse me. So a little bit as a reminder, I mentioned tiles, and I mentioned a tag directory. I don't believe I mentioned a quadrant before. So the memory hierarchy that we have here on Theta on KNL is you have a DDR4 with 192 gigs per node, and you have 16 gigs of MCDRAM on chip. And then you have the tiles have their own L2 cache, and the cores have their own private L1. I just want to set up some definitions here so that we don't get confused in the next slides. So a tile is the set of two cores. They have a shared 1 meg L2. A quadrant is a virtual concept. It's not a hardware property per se. It's a way to distribute the cores in different quadrants, essentially dividing the processor in 4 quadrants at the logical level, right? Well, actually not divide the cores, divide the tiles. The tile would be the minimal unit for assignment. In the case of Theta, when you look at quadrants, they're all balanced because they all have 8 tiles, 16 cores each, right? In other systems, you might end up with quadrants that have sort of 9 instead of 8, so they will end up with 18 cores in one quadrant and 16 in another. And the difference will be very minimal. On top of these tile and quadrant concepts, we have the tag directory. And the tag directory essentially tracks the cache line locations in all L2s, so that when there is a request, it knows where to send you to grab the information, right? So how does this break down? We have 2 main types of memory, 3 memory modes, cache, flat, and hybrid. And we have multiple hybrid choices. Now, I have never played with hybrid mode very much, so if you have deep questions about hybrid mode, I will have to take those and get back to you later. But the setup is pretty straightforward in theoretical terms. With cache mode, you just have an invisible cache, the same as your L2 or L3 cache in your processor. You don't actually write to it directly. The system is continuously caching the more frequently or the used data, right? So in that case, you just see the DDR4, and the system takes care of caching stuff for you. And the effect of that is to see a much higher effective memory bandwidth than you would normally see if you just have DDR4. But from the programmer point of view, you have to do nothing. In flat mode, you have 2 separate memory spaces. You have to explicitly tell the system where you want to run your memory allocations and so on. Do you want to do it in DDR4? Do you want to do it in MCDRAM? And hybrid is obviously a hybrid mode where you can choose a fraction of the MCDRAM be set aside as cache, and the rest of the NCDRAM be used as a direct access mode. Now, the memory modes, what they do is they determine your overall memory layout. And all I have here is the description of what I just told you. NCDRAM acts as a cache in that first. The only thing I didn't say is that it's directly mapped, so you could suffer conflicts, but it's typically so large that it doesn't become an issue, and you don't see it as a user. It's just not even there. In flat, but you can use NUMA control or Menken to decide where to place arrays, and I will cover that in the next slides. And hybrid is just that mix of the two. Now we also have cluster modes. And cluster modes essentially determine your L2 traffic flow for coherency. I'm saying there's 3 supported modes. There's 3 principal supported modes. There are other modes that are supported, like hemisphere and so on, but they all map to one of these with slight modifications. So if you understand these 3, you understand all the available memory modes for Cdrom. So we have all-to-all, quadrant, and sub-NUMA cluster, and that's essentially an increasing level of complexity. But I'm going to describe how those works next. So in all-to-all clustering, you essentially have no affinity between the tile, the tag directory, and the memory. So if you have an L2 miss on a core somewhere, you would have to potentially traverse the whole mesh, well, not the whole mesh, but to go to the other side of the chip and then go back to the beginning to grab information from memory. So you're not guaranteed locality in any of the 2 steps. In the quadrant configuration, you don't have affinity between the tile and the tag directory, but you have affinity between the tag directory and the memory. So it shortens one of the 2 paths, right? When you have a miss, you might still have to go to a tag directory location that is reasonably far, but once you're there, the data is actually very close. It corresponds to the memory controller that is associated to that quadrant. So this potentially reduces your overall coherency trip. In NUMA clustering, you actually divide this chip into 4 different NUMA nodes, at least 4. What you have is affinity between both the tile and the directory and the memory controller. So you shorten in both trips, because if you have an L2 mesh, immediately you know that it's going to be in your quadrant. You don't have to go any further than that. And not only that, but the memory should be associated with the controller on that quadrant. And you have 2 options for this, SNC2 and SNC4. SNC stands for sub-NUMA clustering. And I'm going to tell you how those look in the next slides. So if you want to see what your node looks like and what the memory structure looks like, the easiest thing to do is just use NUMA control -H. That will show you essentially what you have. In very broad terms, on cache mode, you're going to see MCDRAM as an L3 cache, so it's not going to show up on NUMA control. And SNC2 and SNC4, you're going to see between 2 or 4 MCDRAM NUMA nodes and 2 or 4 DDR4 NUMA nodes. On all the cases where you have more than one NUMA node 0 is the default allocation location and corresponds to DDR4. And the reason that was done, you might think, well, HBM is faster, right? Why is that not the default? Well, the reason that's not the default is that typically DDR4 has a larger capacity, and so you're going to experience less issues with, say, oh, I ran out of memory because I allocated this gigantic 30 gig array or something like that. So it's mostly for safety. But you can control how all of that takes place. So the simplest possible setup you can have would be a cache all-to-all or cache quadrant setup. And if you did NUMA control -H, this is what you would get. You will see that NUMA node, there's only one NUMA node, number 0, and all the processors are associated with it. I mean, all the cores are associated with it, and you can see the total size is 192 gigs. The list there is listing every single logical thread ID from 0 to 255. And on red on the top, you have the right way to ask for this if you submit a job with Cobalt here in Theta. Don't worry if the writing is too small, that you could get it from the slides later. If you have cache on SNC4, for example, you will see a very different image. Now you have 4 NUMA nodes. You don't have anymore because all the MCDRAM is in cache, so you're not going to see it. Each of these 4 NUMA nodes should have 48 gigabytes associated with it for a total of 192. I will skip one of the nodes, node 3, because I didn't have enough space. And you will see that the actual logical threads have been assigned to the 4 different quadrants in this case, right? The 4, not quadrants, the 4 different NUMA nodes. So this brings up the case of, okay, what am I going to do with Affinity when I have things like this, right? Which is a concern. Now, if you move to flat space, where you can directly address different things, in the simplest case, which is a flat all-to-all or flat quadrant, you're going to see 2 different NUMA nodes. NUMA node 0 will be your DDR4 with 192 gigabytes, and NUMA node 1 is going to be MCDRAM with 16 gigabytes available. You can see there's not assigned CPUs to node 1. You would always see this with NUMA control -H. They're going to be the same nodes that are assigned to node 0. So any of the logical threads has access to both node 0 and node 1. For flat SNC4, things are a little bit more convoluted. You can see that now we have a total of 8 NUMA nodes. You have 4 on DDR4. Again, each of them 48 gigabytes inside. And then you have 4 on MCDRAM, each of those about 4 gigs inside. So you can see that if you really want to play with flat SNC4, you better have a very good reason to do it, because things can get a little bit out of hand, right? Particularly when you look at some of the performance differences with just playing with cache or with quadrant, where you can see that unless your code has some very specific characteristics, the overall performance changes are not going to be tremendous. So a split, which is one of the options you have here on Theta, divides the MCDRAM into a part that is assigned for cache, which is I think it's 25%. Yeah, 25%. And a part that is assigned for direct access, which is the 75% remainder of the MCDRAM. So you're going to see 2 NUMA nodes, the regular DDR4 with 192 gigabytes, and at the bottom you see node 1 with only 12 gigabytes. And that's because the other 4 are being used as a cache to the DDR4. And I would say this is the least common. This hybrid setup is probably the least common I've seen people execute on. Typically, flat quadrant or cache quadrant tend to be the most popular. Now you can control, now that you have a tool to show you how your system is configured and you know how to request that configuration, how do you assign memory, right? So this can be done in multiple ways. One of them, in a very coarse level, is with NUMA control. I can execute something with a membind equals a NUMA node, and memory will be allocated there. You could say just membind to 0, and everything will go to DDR4. And in some cases, that actually makes sense. You have a code that is very latency sensitive rather than bandwidth. This could be a benefit. If you use only MCDRAM because you know you fit inside the 16 gigs and you're not going to have any problems, you can say membind equals 1. The problem with that is that if you did not fit for some reason. Say your arrays were a little bit larger than you expected, or you missed when you were sort of evaluating how much memory you were using, you missed something and you went over 16, then you're going to have a hard crash because there's nowhere else that you can allocate memory. You've told NUMA control only to use node 1 and nothing else. So if you have more than 16 gigs and you use membind, that's going to fail, which is not a bad thing. At least it tells you you're not running in the place that you thought you were running. Something safer but less, possibly less performant is preferred. With preferred, you can say preferred equals 1. So I would like you to start allocating memory in node 1. And if you run out of a space there, just move to node 0 and keep going, which seems like a good idea, but it could bite you in terms of performance because you have no guarantee that the arrays that use the most bandwidth in your code are going to end up in MCDRAM, right? This is just saying the first allocation goes to MCDRAM and keep going until you run out of space. It's not telling the system, hey, I have a lot of L3 misses when I access this particular, well, in this case, L2 misses. When I access this particular array, I want you to put it in MCDRAM. It is not doing that. It's completely blind to the performance characteristics of your code. Now, that has a fix. You can always use memkind to specify which arrays go where, which is what I'm going to cover in a couple of slides. And if you don't know what arrays are using most of your bandwidth, btune has a memory access collection, which is a type of analysis that will show you which of your arrays or data structures in general, they don't have to be arrays, are consuming the most bandwidth in your execution. And so you could go and just gather those and say, okay, so these are going to go to MCDRAM. You could just estimate the size to make sure they fit. And if they do, you can use memkind to allocate them on MCDRAM and let the rest of your code run either in MCDRAM if it fits or in DDR4. And so you will be taking all the advantage of the performance of the bandwidth in MCDRAM, and you would still be able to execute your code. But that takes a little bit more work because first, you need to be aware of which data structures are using most of your bandwidth, and then you need to modify your code to include memkind. Node selection for SNC2, SNC4, it's a little bit more convoluted. You could do something like this, but it's really not ideal because you're just saying put it on those NUMA nodes, and you might still have a lot of traffic across them. And so it doesn't seem to be, I'm thinking just of a purely threaded code, right? You could be forcing essentially non-local memory accesses by doing this. If you're using just pure threads, you can't really use the APRAM-S option to fix this. If you're using MPI, that might be a way to fix it, where you place, say, an MPI rank on each of the NUMA nodes, and then you just control affinity under that for the threads that go under that MPI rank. And so in that sense, APRAM-S will help you because it distributes your ranks across the nodes. So that's something you might want to look into and understand when you launch your codes. Although, like I said, at least from my point of view, cache and flat quadrant are probably the simplest to use and get you within a small fraction of the performance that you get by doing all this complicated stuff. But in some cases, you really want to do it. And now, I have a few more minutes. I'm going to cover memkind pretty quickly because I don't expect anybody coming out here to just start rewriting their codes, but at least you will have some reference to look at this later. Menken is a library that enables you to control memory allocation, and there are others out there, so you might find something else that you like better. It provides two different interfaces, HBW malloc and memkind, and you essentially have to remember to provide the headers and provide your library in your linking step. Fortran, at least this used to be the case. I have not checked this lately, but Fortran used not to issue a warning if you did not include the library. So it would silently run on DDR4 and ignore all your Menken commands in the code. So that was a problem, and I believe that might still be a problem. So that's something you need to be careful with. Typically, you see such a big performance difference that you'll realize immediately, but something good to know. The changes to your code are pretty minimal when you have simple code that just does regular mallocs, right? All the APIs have very similar structures and names. You will have to include the library, hbw-malloc. You will have to substitute malloc by an hbw_malloc command. But then the arguments are the same. And then you substitute your free by an hbw_free. And this is wonderful because the changes are straightforward, but for some reason the library is called Menken, and then the header is hbw-malloc, and then the API is hbw_malloc. So you have 3 different naming schemes just to do the one thing, right? I find entertaining. So these are the changes for C. In case of Fortran, all you have to do is really use the attribute fastmem, and the system will allocate that on Cdrom. So it's very straightforward. In terms of alignment, you have commands similar to the POSIX memalign command, for example, with ABW, POSIX memalign, and so on. And in general, the functionality covers most of the things that you would normally do with the straight-up arrays. If you have more complex data structures, this can get a little bit nasty in terms of making sure everything is working properly. And this is just for your reference, but you can see that most of the regular sort of C APIs for allocation are covered. And I'm almost to the end. So a quick MCDRAM datasheet usage. You can use membind to run something directly on MCDRAM. And if you don't fit, you will just crash. So you will know that immediately. You can use memkind with that simple interface, and remember to link, because Fortran might not give you an error if the library is missing. Remember, we have 3 basic layouts: flat, cache, and hybrid, which is a mix of the 2. 3 basic clustering modes, out of which I would say the most common use is of quadrant, and the one that gives you the better control is sub-NUMA clustering. So you have a total of about 20 combinations, but at the end of the day, you probably come down to just using 1 or 2 most of the time. And that's really it for this first part. So I hope I covered a little bit of the hardware, a little bit of vectorization. I hope, although I didn't talk too much about threading, you understand how important that is on a processor that has 64 cores and 256 threads. And I covered a little bit of that memory subsystem that is probably the more complex and unusual thing about this processor. And that's all I have for this section. Thank you.